Okay, hello everyone. I'm very happy to tell you that today's class will be something different and exciting. It will be taken by Archit Manas. Archit is a 12th grader from Delhi, Faridabad, and he has represented India at the IMO. He has um, qualified for the IMOTC a lot of times. He is also qualified for the IOITC a lot of times, like the equivalent in informatics. And he has okay, if I list down all of his medals and achievements, it will take way too long. But also, like every class he takes is always something different. So looking forward to seeing what you have for today. Thank you. Over to you.
Thank you for that stellar introduction. Uh, okay, today we'll be talking about sorting. Oh, by the way, if just because so that I'm not teaching to a bunch of uh, pictures, and you guys could turn on your cameras if that's possible. Yeah, okay. All right, so today we'll be talking about sorting. Many of you have probably heard of sorting before. Um, Sorting, basically, maybe you could think of it as you have these numbers, A1 through AN, and you would like to maybe order them in increasing order. Let's assume the elements are distinct for now, actually, so that you're just interested in finding this permutation so that the values increase from left to right. Of course, sorting comes in various forms, and there are many ways to define a sorting problem. Here we'll be focusing on a particular model, which is called the comparison-based sorting model. I'll write that out. So what the comparison-based sorting model is you don't treat the elements that you have, A1 through AN, as any particular values, numbers, or something. You just treat them as they're all this certain type of object. And so maybe you could treat them as these boxes, perhaps. And the way you're allowed to obtain information about these objects is through queries to an Oracle function, let's say. What I mean by that is maybe there's this fictional uh, player, let's call him Bob, who has all the knowledge about these objects A1 through A. And what you can do in a query, you can ask Bob something like I comma j. I is not j, let's say. And what that does is it asks Bob the question: Is AI less than AJ? Like which of AI and AJ is bigger? And Bob, of course, replies truthfully that okay, maybe AJ is bigger, AI is bigger. And the point of uh, sorting is then to maybe ask as few questions as you can and order these numbers from left. So what we would like to do is find algorithms that are able to ask Bob some questions and able to determine ordering for these objects A1 through AN, or maybe do some similar tasks. Maybe we would want to find elements with a certain rank. We could want to find maybe the maximum. Okay, the maximum is maybe a little easy, but we would maybe want to answer questions like that. And we'll be discussing problems related to this in today's lecture. So first, can any of you, okay, so the first thing to determine is to just maybe put into, make it more clear what we're looking for. We're looking for ways to order these elements, and we would like these algorithms that we make to be efficient. So what would it mean to be efficient? Do any of you have some idea what it could mean to have an efficient algorithm? How would you measure efficiency in this case?
The least number of checks.
Okay, right. So one way to measure efficiency could be how many questions do we ask Bob? We could use that as a metric. So there are two ways to think about this. When you look up sorting algorithms online, you'll find that there are two two complexities mentioned, and the reason that is so is because one is maybe the query complexity, So what the query complexity means is number of questions you ask Bob. So this could be one thing you want to minimize. The other thing could be the total complexity. Now, what the total complexity here will mean for us is if I were to actually go ahead and try to implement this algorithm on a computer, how many steps would it take for me to implement this? That would be how well can I code this? Here, we'll be focusing more on the theoretical aspects. As such, we will not be focusing on the total complexity too much. We will really only be interested in the query complexity, the number of questions that we ask for. So you can just forget about total complexity for now, although I will maybe mention it a couple of times when things are a little confusing. Okay, so with that we have a formal setup for what we're trying to do. We would like to find algorithms that are able to determine the ordering of these objects in as few questions to Bob as possible. Okay, so I think I saw that in the chat a couple of people were suggesting algorithms. So, okay. Is this a completely ordered set? Yes, it is completely ordered. So any two elements you give, Bob will tell you an answer. Okay, so can anyone suggest any algorithms that they have to order A1 through AN?
We can do kind of bubble sort.
Okay, how would that go?
Like if I'm not wrong, like taking the topmost element. No, sorry. First, we are checking the first I minus one element, and then we are taking the maximum and then putting it at the lowest level. And then again, we are starting from the first, and then we are selecting the maximum until we have gotten to the. Suppose we had got to the. Suppose we have 6 arrays, and we have got to the fifth element, and now we will go to the fourth element because the last one is already sorted. So
Okay.
like this, we
So,
can sort them.
So what you're trying to do is trying to find the minimum element and sort
No,
of
like the
put that
maximum element.
the maximum element. Okay, so we want to find the maximum element, put that in its correct position, and then recursively solve
Yeah.
for the left over and maximum. Right. Okay. And how many questions does it take to determine the maximum element?
That
What would be the algorithm?
might dip.
So let's say you have A1 through AN. How many queries to find the maximum element?
It was like n minus 1 by 2, yes.
Sorry?
N times n minus 1 by 2. Like the first pass takes at less than n minus 1. Then it goes on n minus 2 and so on till 1.
Right, exactly. So the first
Other algorithm could be like
order and
you
moves.
split the list.
Go on.
Another algorithm could be like you split the list into two halves, you sort each half, and then you merge it in linear time. The two halves with the sorted
That's merge
half.
sort.
Yeah, exactly. So I can see that you all have heard of all of these algorithms. We'll be discussing them for those people who have not heard of them. Okay, so this algorithm, it takes something like O of n steps to figure out the maximum. And the way to do that would be maybe you start with A1 as your predicted maximum. You compare it with A2. If A2 turns out to be bigger, then A2 is now your predicted maximum. Otherwise, you keep A1 as your predicted maximum. And the point is you just continue this process and you ask n minus 1 questions this way because you're going to include in one new element each time. And by the end, because you've processed all elements, your predicted maximum will have become the true maximum. And so that takes order and operations. And as people remarked, as we sum this up over all the layers we have to this recursive process, the total number of steps will be something like n plus all the way to 1, which is n squared. Okay, so we have an O of n squared algorithm. It takes up to n squared steps, and it is able to determine the ordering of A1 through A. Now, of course, the question arises, can we do better? Right? So there were a couple of strategies like merge sort being mentioned. I would just like to maybe focus on the recursive thing for now. Okay. So let's say we have this list A1 through A, right? Now, since we're maybe interested in doing something recursively, we could try something like remove AN, sort a1 through an minus 1. And maybe let's say that the order for those is something like this. And you have an right here, right? And what you would like to do is maybe introduce an into this sorted list using as few questions as possible. Okay. So any ideas on how we can do this?
I guess just check each element. No,
Okay.
like yeah. So you can, or you can, what you can do is check the middle element if the
Binary.
AN is greater than the type of the binary search, I guess.
Right, exactly. So there are two things. One is we could just linearly iterate through this list. So we could check is an bigger than an minus 1. If it is, then we just place it. Otherwise, we ask is an greater than an minus 2. If it is, then we place it right after an minus 2, and so on all the way till a1. And then if an less than a1, then we just put it to the left of a1. And this takes, of course, up to order n operations. And you'll find that if we were to simply repeat this, it would take up to O of n squared steps. And as someone already mentioned, we can actually optimize this part where we specifically search for an's position using something called binary search. I'll just sketch the idea so that it's clear. So the idea is we have these elements. Now let's say we look at the middle element, maybe floor of a n minus 1 over 2. And what we do is we compare an with this middle element. If an is bigger, then we certainly know that an's position belongs somewhere in this array. And so we have sort of half the size of our problem. And on the other hand, if it turns out to be smaller, then also we have half the size of the problem roughly. And because we're halving the size of a problem each time, there were n elements originally. And so this takes up something like log n steps to get to the exact position that n belongs to. And so that takes something like log n steps to figure out n's position. And then if you sum that over from 1 to n, you would get maybe something like n log. But to be more precise, you would get something like log 1 plus log 2 all the way to log n. And then maybe you just put ceiling everywhere just to make it precise. This is, of course, log 2. And that would be maybe something like log 2 n factorial plus maybe something like n. So we have this algorithm that is able to actually find this ordering recursively by using a binary search in the recursive step. Now, one question you would ask is, okay, sorry. So this is called insertion sort, or some of you may have heard of it. Some of you may also remember that insertion sort takes n squared in the worst complexity. Well, what that n square really is talking about is the total complexity. The query complexity is still this, because if you use a binary search, then you're able to reduce the query complexity to n log n or log 2 n factorial, something like that. But the actual total complexity of actually, being able to reorder the elements of the array in any way you like, that's a little difficult to do on an actual computer where you're trying to write code for solving this problem. And implementing that is actually really hard without already using something like sorting. And so it becomes very roundabout in that sense. And so therefore, insertion sort is generally just said to have quadratic complexity because that's the total complexity. And in real life, in real world settings, we often care about total complexity as well. So that was insertion sort. Now, sorry, so I think some people have been writing things. Okay, good. So that was insertion sort. The next thing we're going to be discussing.
Wait, what's the algorithm for insertion sort?
Right. So we just discussed this. So the point is you remove one of the elements, say an, and you look at an through an minus, and let's say you recursively solve.
Okay, this is only insertion.
So that takes maybe like t of n minus 1 steps. If let's say t of I is the number of steps it takes to sort, or number of questions we need to ask to sort I elements, and then we just prove that t of n is this plus O of log n. And so if you just add that up, that comes out to O of n log n. Okay, so that was insertion sort. Next, we're going to be discussing merge sort. Now, I think someone already mentioned using merge sort. I think it was Athar. Okay, so yes, next we're going to be discussing merge sort. I imagine quite a few would have heard of it already. The idea behind merge sort is we have this problem of size n. What we do is we break it up into equal size. So maybe like look at something like the left half, the right half. And what you do is you sort this. So you recursively call your own procedure on these. And so you're able to like sort of sort both of these. And then the question becomes, you have these arrays. I'm just going to call them with different names now because really this is the only problem that we need to solve. You have, let's say some sorted sequence of length X and another sorted sequence of length Y. How many questions do you need to ask Bob to actually merge these two sequences into one sorted list? Can anyone tell me an algorithm that would do that?
We can do the same thing as earlier, just first put B1, and then we can know that we can just say that B2 obviously comes after B1. So like we take the elements after B1, and then we do the same thing as insertion, and we insert B2 and we do going
So
right.
you mean to like sort of binary search for B1's position in A1 through AX?
And then you consider only the remaining stuff. Or you can actually also just do double binary. Like you can take the middle of B1 to
Can't we
BY.
just like,
Right, you can take
can
all
we
the
not
These
just
are all very
compare
interesting
like
case.
A1,
Let's go over these.
B1?
Yeah, sorry, go on.
We just compare A1, B1. Then which one is first? Then we compare the other one with second, and so on.
Okay. So just to maybe make things a little cleaner to understand, let's imagine A1 through AX as our base sequence. So this is the sequence that we'll be adding B1 through BY into. So let's say that BI's true position is right between ACI and ACI plus 1. So there's the sequence CI, that would be the list of correct positions that we need to introduce. And of course, it's possible that BI actually belongs right after BI, in which case it's sort of invalid, but bear with me for a moment. You want to basically find the sequence CI. And the idea is the information that you have from B1 less than B2 all the way to BY is that BI will certainly show up after BI minus 1. As Shreyan already said that before. There's one thing we could do. We could just sort of repeatedly do a binary search to figure out B1's position, and then do a binary search on the restricted thing, and then another binary search on the restricted thing still. And we could just keep
Would
doing
it
that.
be better to do binary search on the middle element in the B sequence? And then
and then we
Okay.
have.
I'm not sure why, but it seems
Are we assuming that
like
B1
it's usually somewhere in the middle, so it will split it properly.
Okay. So what could always be the case is that this left half that you've sorted is actually like maybe all of these are smaller than the right half, right? So this is always possible. And then in that case, looking at the middle element or any element at all is not going to be really splitting A in any nice way so that we can develop these recursive procedures. So that's not a very useful strategy initially. Of course, it works and it gives us a complexity of something like y log x because it takes up to log x operations to introduce x. Actually, it's not going to be y log x. It's actually going to be y log x plus y because the size of this list also increases as B1 grows.
Yes.
Okay. So this would take something like y log x plus y steps. Really, I'm just going to call this as x plus y log x plus y. So let's say the total number of elements here is n, maybe. I'm just going to call x plus y equals n. And so this takes something like O of n log n. Can't say much better. But somehow the thing we're not using very well is the fact that these are ordered. We do not need to do a binary search. And the reason that is because x as a sequence is probably similar size as y. Let me explain that. So if x was really big and y was really tiny, then it would make sense to do this binary search. Because there's such a huge space and you're just trying to figure out B1's appropriate location. But when B1 through BY and A1 through AX have roughly the same size, it actually makes sense to just continue doing what we were doing earlier, but linearly. What that means is you have something like A1, A2, all the way to AX, and then you have these interstitial spaces where B1 through BY can now fit. And what you do is you ask a question between A1 and B1. So let's say you just keep asking B1 through A1, B1 with A2, until you find that, okay, so B1 was less than AI, some AI out here. And so it sort of belongs right in the middle of these two. So you just appropriately fix B1 in here.
For B2, you can just start asking from AI.
Exactly. You can just start asking from AI. And so now, you don't need to ask about A1 through AI minus 1 because you've already done that. And now if you think about this, can anyone tell me how we can estimate the number of questions we ask this way?
Around we y by x into y square by x around
Sorry, go on.
y square by x, I think,
Y squared by X. Why do you think that?
because we have x terms and we want to put y over there. X by x only. Sorry, I didn't speak. X only because you have x terms and you have y things. So on average, the density will be x by y. So you have to ask x by y questions on average, and you have to do that y times. So x by y into y equals to x.
Okay. So, well, there are certain problems with that analysis. For example, it just assumes that it's going to be average distributed. That need not be the case. B1 could be bigger than multiple elements of A1, but then you're able to figure out B2 very quickly after you figure out B1. So, of course, all these are not necessary. What we will simply do is think about the questions that we asked with B1. Which AI did we compare B1 with? So if you think about that,
Is
we
it x
compared B1
plus y?
with some interval. So we compared them with 1, 2, all the way till maybe I, A1, A2.
Is it x plus y?
Yes, it is. It is linear. That's yeah. Okay, so let me just explain. Let's say B1, you ask questions about B1 with all AT from 1 for T in 1 to I, right? And now the point is, when you think about BI plus 1, sorry, B2, you will ask a question for B2. You won't ask a question, sorry, for B2 with AI minus 1 because you already know it's bigger than that. Because B2 is bigger than B1 and B1 is bigger than AI minus 1. You know this, so you won't bother asking with this. But you don't know about AI. It could still be the case that B2 fits right in here, right? So you do need to ask AI. And so you ask B2 with AI, and so you could have potentially this intersection, and then it will just continue increasing all the way again, right? And then the next sequence could also potentially overlap with the last element, and it would continue so on. And if you think about it now, you're only going to ask with up to X things. So really the union of all of these intervals is just going to be maybe something like, it's going to be bounded by 1 through X. And these repeats that we see, these indices that you could potentially query twice, these are precisely like, there is like a one-to-one correspondence between these indices and elements of B1 through B1, because the place where you ended for BI minus 1 is where BI would be questioning again. And so you have up to Y of these repeating indices. And so because the total union is having size X and the union has size Y, the total number of questions we ask is bounded by X plus Y. And so the total algorithm is linear. So note that here something like X log X plus Y, sorry, Y log X plus Y is much better only when Y is really, really less than X. So if Y was something like 1, then log X is really good. You would not want to do something like X plus Y here. But the point is, because you already have the order for Y elements, as Y becomes larger, that's more and more useful information. The fact that you know Y things and how they're ordered. And so you use that using just the linear setting. This is also called, well, a two-pointer algorithm. So we have these 2 pointers. One is the B1 that we're working with, and the other is the A1 or the A2 that we're going to be comparing with next. And so, the total complexity of this is going to be linear, and that's often. Okay, so that was just a sub-procedure for the process merge sort. So in merge sort, if you think about the complexity of merge sort, then you'd have something like T of n is equal to something like 2T of n over 2, because it splits roughly into pieces of size n over 2. Actually, I'll just not do this. I'll just call it T of A plus T of B to be precise, where A and B are both roughly n by 2. There'll be some off by 1 error. We'll take care of that. And plus you have something like order n. Is it all clear so far?
Yeah.
Why the plus order n? Won't it be plus order 1?
Sorry?
Why the plus order n?
Why did I?
Why you put plus? Oh, yes.
Because you take up to linear steps to actually merge these two sequences, right? You'd need a linear number of questions.
Why n be approximately n by 2?
Because that's up to us, right? How we split the problem size. So
Okay.
we chose something like roughly half. middle of the pack.
Okay. Yeah.
Okay. So you get this recurrence, and the question is, how do you solve for this recurrence? So here we're going to build the recursion tree. And what that means is you have a problem of size n, and that sort of splits into problem of size A, problem of size B, and of course this will split to 2. And the cost that you incurred in this splitting step, or not the splitting step, rather the merge step, actually merging these two, we write the cost of that on the vertex itself. So this is something like O of n. That's the amount of cost it takes to actually figure out n. And now this will also incur some cost. It'll in fact incur O of A, O of B, and you're going to just split into this tree, and it's just going to proceed all the way down. And then the leaves are just one element problems, and then they have zero cost. They really don't cost much. You could even treat them as maybe order 1 cost. Now the question is, you would like to estimate the sum of weights assigned to each vertex of this tree, because that's the total complexity of your algorithm, right? And the way we do that is by going layer by layer. So let's say you look at the top layer. The top layer takes O of n operations. The next layer takes O of A plus B operations, but because A plus B was n, that's actually just order n operations again, right? So if you call this layer L1, that takes O of n steps. Look at L2, that takes O of n steps as well. If you look at L3, then you'll have maybe A split into A1, A2, but then that sums to A again, and B1, B2 also sum to B again, and then that completely sums out to n again. And so this is also order n steps.
So we have O of A plus O of B as O of A plus B.
Sorry?
O of A plus O of B is O of A plus B.
Yes, of course. Right? If you're bounded by C1A and you're bounded by C2B, then their sum is just bounded by max of C1, C2 times A plus B.
So then overall this is O of n square.
Well, yes, because the height of the tree could be up to n. But there's a key
No,
observation.
right? It's
Log 2n.
why would
We're
it be up
splitting
to n? It can be log n.
Yeah,
Yeah,
log
Yeah.
exactly. Because we're splitting into half, we can actually bound the depth. I mean, at
Right.
surface, it just appears, okay, this could go on up to something like n because you're only strictly reducing n each time. But now we're going to actually justify that the depth is actually bounded by log. And the reason that is so is because if you just think about, so obviously, if A is at most B, then A's depth can't be larger than B's depth, right? That makes sense. And so you'll just descend into the larger. So if you just keep descending into the larger thing, you can see that you're sort of changing n into CL of n by 2, right? And you can just prove very easily that this operation is something that stabilizes after log n things. It just dies out to 1. And so the depth of this tree that we have is order log n. In fact, exactly log 2n plus some 1, 2, I don't know. And therefore, the total complexity of this algorithm merge sort becomes O of n sum
Log n.
for each level, and that would be n log n. So ordered n log n.
What would the base be in the log?
Sorry.
The base of the log.
The base doesn't matter, right? Because any constant just comes out as part of our bound.
But I think it is 2 in this case.
Sorry, what do you mean by 2n log n?
No, I mean log n to the base 2.
Yes, yes. But of course, it doesn't matter, right? Because, I mean, log 2n is just varying. It's like proportional, let's say, to log n. As long as you have the O sign, it's all fine. Okay, so that was merge sort. Any questions so far? We discussed like 2 very useful sorting algorithms right now. So any questions would be useful now.
Is there a method to calculate a minimum possible number of like exact formula for the minimum number of queries for n? Is there a formula for that?
Well, I don't know if there are explicit formulas. I do not believe there are. I think we know for maybe like n up to 10 or 20 maybe.
Only
But
20.
we do not know the general answer for n, what the exact number of questions is. But then again, in real life applications, you never really care about the exact number of steps. As long as you have something like, okay, I'm able to say something like n log n plus small stuff like linear stuff, you're mostly happy with that.
And how close are we to log 2 of n factorial? Exactly, like how close are we to that exact?
So merge sort is again quite close. If you do a more careful analysis, which I'm not doing here because we're not too bothered with proving something close to log 2 of n factorial, which would be the information
Optimal.
theoretic lower
Yeah.
bound. So Yeah, but this is something like, this is close to n log 2n. This is like n log 2 of n factorial plus O of n.
Wait,
Merge
why
sort.
do we care about log n factorial?
All right, so I'll get to that next. That is our next point of discussion. So the next point of discussion is, okay, so we've discussed sorting that does it in O of n log n, but why n log n? Can we not do better? And in fact, I think a couple of people were again talking about this in the chat, but yeah. So in fact, we can show that we require at least any sorting algorithm needs at least log 2 n factorial steps to figure out the order. And again, the way to actually think about this is to think about the game rather from Bob's perspective. Every time we ask Bob a question, Bob reveals some information. Bob tells us that x is less than y or y is less than x. And so Bob's, if Bob were adversarial in the sense that he's trying to delay us finding out the order with as few questions as possible, he would try and answer in a way so that the number of questions we ask is quite large, right? That's what Bob would try to do. And that would be the worst case complexity of any algorithm that we do, right? So let's say that we have some algorithm. I'll just quickly show how Bob can ensure that the game goes on for at least log 2 of n factorial turns. And that will be fine. So here's what Bob does. Bob does something like, he has this entire list of valid permutations that could be the hidden ordering. So he has like something like n factorial permutations and the set S, right? At the start of the game, the permutation could be any of these. And now questions arrive from the algorithm, whatever is solving this and asking Bob
I
questions.
see. So what's happening is that each time a question is asked, you can only like preserve like half of the information, and then like the other half of the cases kind of get discarded.
Yes, sort of. So like Bob sort of just chooses the more frequent options.
Basically, it takes log of n factorial bits to figure out the permutation.
Yes. So the idea is initially Bob starts off with S. And so let's say S is something that both Bob and the algorithm would know technically. Know is in the sense that, okay, if you could somehow actually list out all n factorial permutations, then the algorithm too would know, because the algorithm has asked a set of questions and they know the answers to that. And so based on that, you can discard the inappropriate permutations. And therefore, both of these players, the algorithm and Bob, have access to S. And the point is, whenever the algorithm asks a question about S, let's say, is X less than Y? Now, there are two ways Bob could respond to this. Bob could say yes or Bob could say no. And there are S splits into these two sets, S yes and S no. S yes meaning set of permutations that still work if Bob were to say yes, and S no is a set of permutations that would continue to work if Bob said no. And of course, we see that S yes and S no are going to be disjoint because obviously you can't have contradictory, you can't have X less than Y and X greater than Y happening simultaneously for any ordering. And so S sort of splits into these two sets, and Bob is basically being asked to choose from one of these sets. That's what the algorithm is forcing him to do. Here, Bob can do something very simple. He can just choose the one that is having larger size. One of these is going to have size at least, one of these will have size at least as half as big as the total set that Bob currently had. And so Bob just chooses this option. And the point is, this ensures that the algorithm cannot discover the true ordering until it has extinguished the size of S to something like 1, right? And now, because it's decaying by a factor of at most 2 each step, each question that the algorithm asks, and we start off with n factorial orderings, you require something at least like log 2 n factorial questions to actually figure out the ordering. Any algorithm needs to make at least these many questions. Okay, so was that clear? So this would be something that's called the information theoretic lower bound. Of course, this does not mean by any means that log 2 n factorial is tight, and there should be algorithms that exist that use exactly these many queries. So this is just a lower bound, and then we find that because n factorial is maybe something like n by e to
Based on
the
the
n
proof
by
of the
6
lower bound, we
doubling.
could find some algorithm, like we take queries so that the space halves, like so that each query gives us one bit of information about the permutation.
But we can't always do that, right? I mean, we have a very limited type of queries. what if none of our queries actually halves the set?
Like our queries is not about passing the feeling, it's just a yes or no. We get some sort of information, whether it's a yes or whether it's a no.
Right. But
So theoretically, so I think it should be possible to create a thing which at least achieves something like log of 2n of n factorial c length.
Well,
but what if our queries don't actually divide into half and half? Like it's possible to make queries which don't divide into half and half.
Yes,
Because our set of queries are very limited.
That's why it comes to us to choose the queries
right.
which
So
divide into
what you're
half.
relying on is that you have this set S of valid permutations, and you're relying on the fact that this has a great balancing question. What that means is the set of linear extensions that you could have if you query two elements, X and Y, if X is less than Y or Y is less than X, you're assuming that you're going to have a perfect split each step. That need not be. There are sets that have bad balance constants, for
It'll
example.
be between 1/3 and 2/3, right?
Sorry. Yes. Well, that's a conjecture. I don't believe it is proven. The best balance constant that we do know of is 8/11. But of course, that's
It has
that's
been
also going to produce a logarithmic.
like it was proven something like 0.3 and 0.7.
No, there are examples of sets that achieve or tend to such constants, but we do not have proofs
Has
that
been proven.
you always find a
It was
compare.
recently proven, yeah.
Yeah.
Something like that. 0.3 and 0.7, if I'm not wrong.
Okay, so anyways, that just tells us that we require at least log 2 n factorial, and so this is very good because now we know that we require at least n log n to solve, and then we also have matching algorithms that are able to determine the ordering of the elements in O of n log n questions. Now, of course, that sort of finishes comparison-based sorting, but now there are other questions you could ask. There are questions like, sorry, I have sufficient time. So one question that is very important is, I have A1 through AN. I'm not interested in finding the ordering anymore. No, what I'm interested in finding is the root n largest elements, let's say, and maybe their ordering and their ordering. So what that means is I'm interested in computing the root n largest elements that this array has, along with an order. So this was the maximum, this is the second maximum, and so on. So it's sort of like sorting. Now, of course, you could always do this by simply sorting the array. That takes something like n log n questions to Bob. And then we just take a look at the last root n elements. And those are your largest root n elements. But we would like to improve on that using the fact that root n is smaller than it, much smaller.
Can't we just do like the insertion sort, but we can, whenever our size goes greater than root n, we can just skip out the first element. Like after we do insertion sort till root n elements, and then we do every new insertion, we remove the first element. And we keep on doing that. So like we insert the last element and we remove the smallest element. And we insert the next element and we remove the smallest element.
Right. So what you're doing is you're suggesting an algorithm that maintains the set of root n maximums so far.
Yes.
Right. Okay. So let's actually discuss that. So maybe you have something like, so you start off with this set. You predict that this is my largest a square root n maximums, and let's say you order them. So you know that this is the ordering, and then comes along a new element, and you use the binary search to efficiently check where it belongs in the sorted order, and then you just remove the minimum. If it's smaller than all of A1 to A root n, then it's not a valid. Then it is a valid maximum because A1 is not then, because A1 is less than A square root of n plus 1, and so you can just extract A1 from this set. Otherwise, if A root n plus 1 turns out to be smaller than all of these, then you just don't add A root n plus 1 at all. And what this does is it maintains this set of size root n, and you know there are something like n minus root n elements present otherwise, and you're going to use something like log root n questions to include all of them. Log root n is really just log n because again this is just going to be half log n, something like that, and those don't really matter to us. And n minus root n is really just again n, and so this is just an O of n log n algorithm again, and so that actually does not improve too much over just sorting the array. Okay. Any other ideas?
Maybe we can break this into root n subsets of length root n.
Okay.
Okay. Order all of them.
Okay.
Okay, and order the last elements basically. Like we put them in a grid, and we order the last elements, and you can just remove half of the elements that way, and we can do something like that.
Okay. So you want to put these in a root n by root n grid.
Hmm.
Okay, and what do you want from this root n to root n grid? So this is increasing, this is increasing, increasing.
Okay, and
what comes next?
You order the last elements of each set, the greatest elements of each set.
Okay.
Okay, and that way you can remove half of the elements in one go, because you know that these elements are smaller than, right? You can just remove the triangle, the lower right left triangle.
Right.
Yeah.
We can also look at like the diagonals of something. So like, and
Okay.
compare
So
the.
Yeah.
right. So let's think about the number of questions we've made so far, actually. So when we split and we made those questions. So to sort this, it takes something like root n log n steps, right?
Mhm.
And then you're doing this root n times, so that's already n log n.
Mhm.
So yeah, we're again not improving really. Look, but these are all great ideas. Yeah. Okay, so I claim you can do it in linear time, O of n. Well, maybe this O of n is hiding a factor, but then it's smaller than n, so you're not seeing it.
Not multiplicative factor.
Sorry?
No multiplicative factor.
No multiplicative factor. Then it wouldn't be right to call it O of n, right?
No, like O of 5n is still O of n, right?
Yes. Constants, yes. Of course, there would be some arbitrary constant in there, but there is nothing like log n, for example. So don't worry about that.
Like we just do we have any algorithm that sorts in linear time? I guess we discussed one.
No, so we just discussed that there cannot be possibly a sorting algorithm that sorts in linear time because we require at
log n.
least log 2 of n factorial questions.
Yes. So like for any algorithm, you need to sort the root 2n. So how will you get a log of linear time?
Well, you only need to really sort the last root n elements, right? How many steps would maybe the root n elements take? That only takes something like root n log root n. That's like root n log n. That is much better than n log n, by the way. This is smaller than n usually, like always. In fact, for large enough n, this is just tiny compared to n.
And we can do that binary thingy. We can just take an element and we can remove half of the lower elements. We can remove all the lower elements, right?
Well,
we can do something like that.
That may be the maximum element, to be honest. And you're not sorting the list. This list is not sorted.
Yeah.
In binary,
okay, so go on.
Yeah, I was like, in binary search, you always need the list to be sorted.
Yes, exactly. Binary search wouldn't be helpful otherwise, because then you wouldn't know that there's a valid placement. Okay, so we're going to revisit one of the ideas that we had all the way in the beginning, finding the maximum and extracting that. That gave us this O of n square algorithm. If we use that, what sort of complexity can we get?
N root n?
Yes, that's right. We can get an O of n root n solution. Or more precisely, if we were trying to figure out the k largest maximums, this gives us an O of nk algorithm. Of course, for k equals root n, this is much worse than what we're claiming that you can use. You can do this in a linear number of questions. This is much worse than that. And so we would like to improve on this. More specifically, the exact thing that we would like to improve on is the extraction of the maximum. That's the costly step, right? It takes us order n time to find the maximum. We want to improve that. We want to find a way to somehow use the fact that we've already compared some pairs before. So, for example, let's think about that algorithm again, the thing we did all the way in the beginning. You have something like A1 through AN. You compare A1 with A2. Maybe A1 is bigger. You compare A1 with A3. Something is bigger. And so on. You continue that way. And eventually you reach AN. Right? And by the time you're done, you have this one maximum and you report that. And you delete that, right? And then you run this algorithm again. But you already have some information. All those questions you asked before, you already know that. So you would like to be able to use that again meaningfully. You wanted to contribute to making it less expensive for you to do that again.
So in the bubble sort, we know that after a pass, the maximum element is at the last. So we can just do root n passes. So like we will have the.
Yes, that's exactly what I'm talking about. That takes order n root n time, which is again much worse than n log n event. So it's in fact better to just sort at that point. So that's not what we're trying to do. What we're interested in doing is finding a way to extract the maximum very quickly with as few questions, like very few questions on average. And the way we're going to be doing that is by developing a data structure for essentially storing all of these objects A1 through AN. Don't get scared of the name or something. I really will not be using any complicated ideas here. Okay, so you have something like this. Let's try to represent the information that we gain by just doing one pass to find the maximum. So let's say you have, I'm just going to call them 1 to n. 1 pi will refer to the object AI. Okay, so initially I compare 1 and 2, right? So let's say whenever we compare u and v, let's say we find that u is less than v, we just draw this edge from u to v, let's say, right? That denotes that u is less than v. This is a way to sort of, track the orderings or the information that we have. So we're going to build a graph, a directed graph, essentially. You have these numbers from 1 to n. Let's say you compare, can anyone just give me a sequence of length 4?
1, 4, 3, 4. Wait, distinct. 1, 4, 3, 2.
Distinct. Sorry?
1, 4, 3, 2.
All right, cool. So we have the sequence 1, 4, 3, 2. So the actual names are 1, 2, and 3, 4. And when we try to find the maximum, 1 is our original predicted maximum, right? Then comes along 4, or which has ID 2, and we compare 1 and 2. And we find that 1 is smaller than 2. And so we draw this edge from 1 to 2. Then comes along 3. 3 has value equal to 3. We compare 3 to 2, but it turns out that 3 is less than 2 as well. And so we draw this edge. Then finally, we need to test the last one, which is 2 with ID 4. And we find that it's smaller as well. And so we sort of get this, right? This is sort of like a directed graph that we have by the end. And from this, we can sort of figure out that 2 is unequivocally the largest element in the set of 4 elements that we had. And so you can sort of just extract 2 now because you know that's the maximum. Right, so this gives us a way to find the maximum using order of n questions. The point is when we delete 2, for example, in this particular example, it's so bad for us, just think about that once we remove 2, all of those edges go away as well, and we're left with no information. We want to avoid this. We want to ask these questions in...
Sometimes the maximum switches, right? Like if you have multiple maximum switches, we get certain information that a certain number is maximum in a certain subset.
Yes, exactly. And
we
we would
get
like
some
to
sort
make
of
use of
tree.
that. Yes, that's right. Well, it didn't happen here because the maximum appeared way too soon. But yes, ideally that is what we would be interested in having eventually. Okay, so now this is the magic step, let's say. We're going to be defining a sequence of trees. So this is like sort of like a hint to solving the problem. The trees are defined like this. So T1 is just a tree on one vertex. All right. These are all directed trees, by the way. Then you have another tree T2, which is defined as a T1 pointing to the root of another T. Can anyone tell me what T3 would look like?
T1 pointing to T2.
No, T2 pointing to T2. So we're just like sort of doubling each step. So this was like one T2 and this is another T2, and you just point one root to the other root. All right. Then we're going to be defining T4 as
T3 like pointing towards T3.
exactly. And you can see that this is going to take very long to draw. Okay, that does it. All right. So is this clear?
Yep.
Okay. Actually, let me call this T0. Makes things easier. So T0, this is T1, this is T2, this is T3. So can anyone tell me how many vertices does Tn or Tk rather?
2 to the
2
K.
to the power k.
2 to the K, right? Because each step we double the number of it. We double the number of
What are
vertices.
the vertices again in the graph? What do
Sorry?
they represent? The vertices represent the AI,
The
right?
numbers, yes, the AI, yes. And the edges represent the information that we have about.
And what do we define TI as?
Ti is defined as a Ti minus 1 pointing to another Ti minus 1. And this connection is between the roots, the two roots of Ti minus 1.
Okay.
All right. Okay, so that defines these trees. These are called binomial trees. And we're going to be using this to devise an algorithm that does it very well for us. Okay, so let's just quickly see some properties of Ti. What degree does the root have?
I.
Yes, that's exactly right. It's I, because T0 is 0, and then you can just prove that by induction. Like if the root had degree I minus 1, and then because the other Ti minus 1's root added an edge to this current vertex, now that's going to have degree I. And so this is I. The next question I want to ask you is, what happens when I delete the root of a Ti? Ti minus its root. What does that look like?
Ti minus 1 plus Ti minus 2 plus dot dot.
Yes, very good. Bingo. That's going to look like Ti minus 1. The reason that is because let's say I look at Ti, it looks something like this, right? When I delete the root of this, first of all, this splits off. This just becomes Ti minus 1 because that thing was completely different. And now I'm just in this procedure where I'm removing the root from Ti minus 1. And so this just splits into Ti minus 1, Ti minus 2, and you'll find that this goes all the way to T to the 0, which makes sense because the number of vertices is preserved as well. This was 2 to the 0, this was 2 to the 1, all the way to 2 to the I minus 1, and that sum is just equal to 2 to the I minus 1. Exactly one vertex less than the number of vertices that Ti has. Okay, so now you have these trees that have all of these properties. So the important properties are Ti has 2 to the I vertices. Root of Ti has degree I. When we delete root of Ti, it splits into Ti minus 1 all the way to T. So these trees satisfy these properties. And now I would like you to use these trees to construct a way to actually store the information so that you can continuously extract maximums very cheaply.
Can't we just have worst case scenarios of maximum happening at the start?
Sorry?
Can't we just have worst case scenarios of maximums happening at the start, like a completely unsorted list?
Okay, so that just means that you have to change the way you're merging. Don't ask questions like, I'm just going to find the maximum in one linear path. Don't do that. Do something better, maybe. right?
So a TI's root has I vertices. I.
Degree I,
So
yes. In degree
degree
I,
I.
in degree.
Yes, degree I. And we know that when a element points to another, when a vertex points to another vertex, it means that it's bigger than that. So I guess we have to take the vertex with the maximum degree, which will be the maximum, I think.
Yes, something like that. We want to use the fact that in a certain tree Ti, the maximum is its root. That is the key detail that we must somehow
Are we
incorporate.
allowed to assume that n is a power of 2?
No, we will not be assuming that. You don't need it. It's clean enough.
Can I just do like I compare the first two elements, I compare the next two elements, I compare the next three elements to get T1s, then I compare that again to get T2s and so on?
Yes. Yes, these are very good ideas. So what we're trying to do is we're trying to mimic the TI in our way of asking questions. And the way we do that is initially we start off with everything like till a bunch of ones. And what we do next is we compare these two. These are both T naughts. They all start off as T naughts. And you can merge them and they become a T1. Right? These two will merge and become a T1 too. And you get a bunch of T1s. And then maybe you have one T naught left, who knows? And then you merge these T1s again, and you just keep doing that. Right? When you have two T1s, you merge them to form T2s. And if you have two T2s, you just continually merge them, let's say. And how are we merging? Let me define that. So you have this root Ti, and a merge of these two is defined as just asking Bob about these two vertices. Which of these is bigger? If you find that this one is bigger, then you just draw this edge to get a Ti plus 1. Otherwise, you draw the opposite edge, reversed edge to get a Ti plus 1.
Wait, how many moves would we take like to take two T1s to T2?
Right, so we'll discuss that. So there's a very neat trick there. So let's say eventually this process will stabilize, right? Can anyone tell me what the largest value of I could be, such that there is a Ti?
Lower log.
Yeah,
log
n base 2.
Up to log 2n, right? It can't be too big.
Yeah.
So basically you have something like you have up to these levels, these layers of trees based on how big they are. So this is maybe the layer for size I equals log 2n seal. This will be maybe empty, or maybe not empty, maybe it has something like one tree. Okay, maybe not here because that would actually just kill off all vertices, but yeah. And then you could have something like I minus 1. So you have these layers essentially from, I'm just not getting into floor logs. Let's just call this, you have log 2n, log 2n minus 1, dot, 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 all the way till 0. So you have these up to log n levels, right? How many, and what I mean by a level is, let's say level I has trees of form Ti in it, all right? So how many trees could a level have? One, up to one, right? It can't have two, because if it had at least two, then I could just merge some two of them and push it up to the upper level.
So like this
right?
is the base 2 representation of L.
Yes, it would be the base 2 representation, but we won't be needing that. But that's a good observation. Yes, that is exactly what's going on. So you have these levels, these layers, and what you know is that in each such level, layer I, there could be a Ti or there is no Ti. There are two options, right? Two possibilities. There is a Ti, there is no Ti. And now what we would like to ideally do is somehow be able to actually extract the maximum from this, right? How do we do that? How do we find the maximum?
We will have a log n comparison operation, but that's slow because we're looking for n steps.
Okay, so actually let's ask that first. How many steps does it take to actually make this structure?
N minus 1, max.
Yes, it would take order n operations. And the way to think about that is to define a potential function as the total number of components. The number of connected components, when each time we make a merge, that reduces by 1. It starts off as n, and so we make up to O of n operations in this. So in linear time, we're able to construct this structure, right? And now, how would you find the maximum from this?
I could just compare all of these roots, like all of
Okay,
these
so
log 2 and
instead, let's think about it this way. Who are the potential maximums? Who could the maximums be? Like, where are they?
log 2 and roots. Like you can
They'll
just compare the
always
log
be
2 and
the
roots.
maximum of each sequence.
Sorry?
They'll just be like the maximum term of each sequence.
Exactly. So if you have these trees, Ti1 through Tik, then only the roots of these Ti's could potentially be the maximums. It can't be anything else, right?
Yeah.
Do you agree?
Yes.
Okay. So we have up to K, which is actually log n. So we have up to these log n potential maximums. So these are like, sort of like shortlisted candidates for which of these people is going to be the maximum. And how many questions does it take to actually determine, to actually ask around and find out which of these K elements is the maximum?
Is it a better idea to just do the normal method, or is it a better idea to do this recursively, like log 2, like you can recursively make, what did you call it,
No,
binomial
don't
trees?
do that, don't do that. Yeah, that will be too complicated, and it won't actually improve the runtime.
And we could just do like linear checking, I guess.
Okay, so how many questions does that take?
Log 2 and max.
Exactly. So this takes order K, which is actually order log n questions, and we're able to actually find the maximum, right? Okay, cool, we found the maximum, but if you think about it, it actually took O of n plus log n. So it's still linear for finding the maximum. Why is this any better? And the reason this is better is because let's say that the root of Ti existed in level I. Let's say this is level I. So, you have, let me remove the middle thing. So you have one Ti, right? And now because we found the maximum, we will just extract it, right? We don't want it to remain. We want to now find the new maximum of things other than this. And so what you do for that is you simply delete that from Ti. What happens to Ti now once we delete the root?
It turns into the lowers.
Exactly, it turns into the lower. So what you're going to see happening is that each of the lower levels, they all receive one tree. And what do you do now?
You combine them. If there are two in the same level, then combine.
Exactly, you just keep combining them again, and you again get this very you just reach this structure again. And what you do now is again just to find the next maximum, take O of log n questions and extract it. So how many steps does it take to actually find the maximum? So like if I want to find the first maximum, how many steps does that take?
Log n.
Log n. The second maximum, still log n, and so on. But where's the real cost? The real cost is in this remerging now, where we're actually, finding a way to merge these components again and again, and that might cost more queries. And that's what we're going to be looking at now. So far, we know that building the original thing cost us n, and querying for each of the k maximums, or root n rather, cost us n plus something like k log n. What we're interested in now is those remergings. How much could that have cost us? And so to look at that, we're again going to look at the number of connected components. That's going to be our potential function.
Wait, how was it initially n? Isn't it O of n?
I mean, yeah, I'm sure. I mean, this is all under O, of course. Anyways. So let's say the number of connected components is equal to C. What's C initially? N. C at all points is, of course, at least 0, right? And here comes the crucial step. Each time I delete a certain vertex, a certain maximum, what happens to C?
It increases by I, where I is the Ti.
Exactly. Okay, so it increases by up to I, right? Where you have something like this level Ti.
Does it not decrease?
No, C will increase, right? When we split it. So if you have something like a Ti and you cut off this, then you actually get more components because all of these become new components again, right?
Oh.
And I, as we discussed before, is bounded by log n. Right?
Yes.
So now I have something like I have increased C by at most log n, right? And so if I do these merges again, how many operations could that take me at most? So I started off.
Log of n plus log n type.
Yes, exactly. Just at most 2 log n, because I had log n trees to start with, up to 1 in each layer, right? And then each time I deleted a maximum exactly once for the current level or for the current maximum that we're trying to determine. And so I increased the number of connecting components by log n. And so now I have something like up to 2 log n components, right?
And you need log n merge operations.
We will do up to 2 log n merge operations now, because that's how many components there are. You can't do possibly more, right? And once I have 2, it doesn't matter. It's all constant. It's going to take, every time I remove a maximum, I take log n to find the maximum, log n questions, 2 log n questions to fix the tree after that. So I take something like 3 log n questions overall. And because I'm doing this k times, the overall complexity will be O of n plus k log n, because I can just drop the 3. It's all constants anyway.
And if
In fact, 3 can be improved a little, but it does not matter because we're only interested in constant anyway. And we have this algorithm that is able to do that. And this sort of a tree is precisely what you call a data structure. It's storing all of this data in a very structured way, so to say. And the point is, okay, and the point here, basically what these trees had was they had great connect disconnect properties. You could connect 2 trees at the same level very easily. And then if you had one tree, when it split into nice describable trees as well. It was not something random. And therefore, because it was so predictable, you could actually remerge and redefine all of these things and actually prove this. This data structure is what is known as the binomial heap, if I'm not wrong, because it relies on binomial trees and it acts as a heap in some sense. It allows you to extract the maximum. You can query the maximum, and you can even extract the maximum. So you can do both operations. You
And
find the
would,
maximum.
and
extract.
wouldn't recursive binomial treeing not decrease the k log n parts?
A recursive, no, it would not.
Why not?
Because, like, think about when you delete that.
Hmm.
It'll take you more time again to remerge all of that.
Not really, because it would only be it would still only take log n operations to remerge.
No, but like when you delete that vertex, you still affect the TI.
Yeah.
Like the actual real level. Like when you deleting a tree from TI, you still get those additional I trees. Still need to merge them. There could be up to log n of them.
Yes.
And so you can't actually like prove that. Even if you're storing this recursive structure on the roots, you have to change that you have to do anyway. But at the same time, you also need to change the lower level thing, which anyways costs more, at least as much. So it doesn't actually make it any cheaper. It just sort of.
And does the depth of this tree ever exceed root n?
The depth of this tree. Well, the depth of this tree, well, it could exceed root n, but that is not a problem, right?
I mean, we could, if it does exceed
sorry, never mind. It can never exceed log n. You can never have your depth exceed log n, because each time you merge 2 things, your depth increases by at most 1, right? The depth of TI is I.
Yeah, and you do that root n times. So the depth could increase to root n.
Not quite. We always maintain that all the trees on the board or in our data structure are of the form sum tx. And because you have up to n vertices, x is utmost log n.
I'm counting the maximas that you removed. If you count the maxima that you removed.
Sorry?
Oh, sorry. So this is very optimal seeming. Like, could you prove this k log n part is optimal?
Well, you can prove k log k is optimal actually, because what I do is I tell you these are the k largest, and now you have to sort them somehow, right? And you can get an algorithm that uses n plus k log k as well, but that's a little more complicated, so I won't be discussing that here. Okay, and this is just linear because root n log n is really small, and so that actually just solves the problem. I believe I still have time, right? How much more time do I have?
15 minutes.
Okay, so I think we can sort of wind up now. We discussed quite a bit. Let's just discuss more about where sorting is going, or like what it looks like at the moment. Sorting is, as you can see, we had all these algorithms something like 50 years ago. We knew how to do it very well, very fast, very quickly, all these things. So
Like we had done like 4 sortings. One is the binary sort, the linear sort, and the tree sort, and one more is the merge sort. So all
right,
of them,
they're called insertion sort.
yeah.
I'm not going to discuss the O of n squared because that's not optimal. We discuss merge sort. We discuss binomial heaps and not binomial sorts. And of course,
Wait, which one? Which one is the binomial? This one, I guess.
Yeah.
Okay. And like all of this have codes that are writable in CP or something. Or only we do insertion sort and merge sort.
yes. Well, if you think about your C++ STL, they've implemented something like a merge sort. It's not strictly a merge sort. They do some other things, but this is all very similar in the way how they actually sort that sequence of integers. So there they also extensively rely on the fact that these are 64-bit integers or 32-bit integers. They factor that into their sorting algorithms, which is why we first restricted ourselves to think about only comparison-based sorting, where these are objects and not actually integers with which you can do all these tricks of, do a radix sort or things like that. So we're looking at this very theoretically in some.
Okay.
Okay. So like I was saying, what comes next for sorting? We've already solved this. Actually, this was solved long back, maybe like around 50 years ago. We already had things like insertion sort, merge sort. We already knew how to do this very well. What comes next? And there is a very interesting generalization of sorting. And I'll just describe what that is, just to give you a glimpse into what sorting will look like maybe. And so far, if you think about it, whenever we were measuring the cost of our solutions by the number of questions we asked Bob, right? But now Bob could make his information priced. What that means is certain pairs of vertices could now be costlier to ask about than other pairs. And of course, Bob fixes these costs beforehand. So what that means is for every single pair u comma v with u not equals v, you have this cost function associated with it, c of u comma v. And Bob gives you this cost function. This is from c something like v squared, s squared, well, let's say s is the set of objects, to maybe r plus maybe. So you have this cost function c, and that tells you how much it costs to actually compare to vertices u comma v, right? And what you would like to do is be able to still find ways to sort by having as few sum of costs as possible. One very important thing to think about here is, well, how do we measure efficiency now? Earlier it was simple, but if these costs are all like maybe 10 to the 10 or maybe even n, I don't know, then the costs will obviously become larger and larger, and then seemingly it seems that you cannot actually it does not seem as though you could possibly hope to get an upper bound on any sort of algorithm. So obviously we need to change the way in which we test an algorithm's efficiency. How good an algorithm is, we need to answer that question differently now. And there are ways to do that. For example, if the one way would be maybe, let's say all the costs are from 1 to m. Can you now tell me in terms of m what you could do, how you could go about solving this with as few questions as possible,
So
or
how
as
does
few sum of
he,
costs?
so how is the cost related? Like, is the cost function very normally, or is it like something like c of u comma v is equal to u times v? Is it the function?
It could be anything. It's just arbitrary. And Bob tells you that. He tells you that my price for this edge is so and so.
Okay. And so
So
when
in
we're
formal
comparing
settings,
stuff,
how you
so
define
could
this is yes, sir.
so could we say that could Bob also say u comma v for all pairs u comma v? Like, if he could he say for like we're only sorting the first n numbers, but what if you wanted to sort the first 3 n numbers or first n plus 1 numbers? And does Bob have a u comma v for all numbers, or does it just have it for u comma v belonging to n squared, n comma n?
Sorry, I don't think I understood that. Could you come again?
I mean that maybe Bob is saying something like, if you have larger n, the mean value of c of u comma v will be higher.
Okay, yeah, that could be true. That could be true. So, for example, some models that are considered are when c of u comma v, this is a monotone function of the values themselves. So like U and V, the actual value. So the value associated in the object. So for example, if A1 is less than A2, then C of 1 comma n is less than C of 2 comma n maybe. So we have these cost models where we assume that maybe the cost satisfies something like this. You could also have something like C of U comma V is U plus V. But this is all acceptable. And of course, the challenge is to sort of try and find good algorithms under such models. But the first thing, like I said, that we need to answer is how do you even say that this algorithm is good and this algorithm is bad? We need a good way to test the efficiency of an algorithm. And the way to do that is more formally, we will define the problem as you're given these costs, you're given this graph, essentially, this weighted graph, which has all the costs on it, and you have this vertex set, which is A1 through A. In one query, you can probe the direction of an edge. Essentially, you ask a pair U comma V, and you get to know which direction it's ordered in. And the task is all about finding the Hamiltonian path. Right? That's what sorting would mean. We want to determine the Hamiltonian path given this, using as few questions or as few sum of costs as possible.
Won't you need a tree, not a path?
Sorry, I mean graph. Sorry, in the graph. Okay, so right. So can anyone tell me a very dumb lower bound for you certainly need to ask this to discover or solve the problem?
Min of C1 comma C2 comma dot dot comma Cn.
Well, no, not quite. Well, really, if the order was something like V1, V2, all that way till Vn, then you certainly need to ask this edge, this edge, this edge to actually say you found the Hamiltonian path, right? There are variants that sort of allow other things, but let's not go into that. Let's assume that you need to ask at least these edges. And so any algorithm, even if it were proceeding by, even if it had like God's luck or something, you would at least need to ask all of these edges. You cannot say otherwise that this is the Hamiltonian path, right? And so you have this lower bound for, the best possible algorithm, which just gets insanely lucky somehow, right? So you have this lower bound, which is the sum of costs along Hamiltonian path. Along P. Some edge UV, and you just so you need at least this much amount of the cost you incur while sorting will at least be this much. And now we measure the efficiency of our solutions by considering its ratio with this sum. And then if your ratio is something like R, then you say that your algorithm is R competitive. So for example, let's take a look at the classical sorting problem. You have A1 through AN, comparison-based sorting problems. A1 through AN, you need to ask a total weight of at least 10 to know the path, right? You must know 1 less than 2, less than 3, and so on. So that requires at least 10. And we just discussed n log n algorithms, right? Because it's a unit cost model, everything costs the same. It costs 1. And so the ratio here is log n. And so our algorithms would be called O of log n competitive. And so in general, the question is, how can we improve this log n? Well, not log n, but what happens in the general case? When the weights are arbitrary, can we say anything at all? All of these questions, they become important. And because even in maybe like real life applications, it very rarely happens that the cost of comparing two things. So for example, maybe in like, maybe very often you'll find yourself comparing maybe DNA sequences, for example, right? And maybe the cost to compare two things is not uniform, right? Maybe it's easier to compare two things. It's not so easy to compare two other things. The list goes on. And in these sort of settings, you want to find new algorithms that still do very well, even though you don't necessarily have this nice fact that every pair costs this. Right. There are some progresses that have been made on this. For example, one version considers that the total number of distinct weights that you have, the distinct weights, we assume that is a W. W is the total number of distinct weights that the graph has. So then we know algorithms that are, I believe, O of n to the 1 minus 1 over 2w competitive. So what that means is that if you had up to two distinct weights, if it was just an A-B setting for some real numbers A-B, positive real numbers, then this would cost something like O of n to the 3 by 4. It would be at most this much higher than the God's luck algorithm.
At most this much or at least this much? Or on average this much?
Sorry?
At most this much higher, at least this much higher, or on
Oh,
average this
no,
much?
at most n to the 3 by 4 times some constant times the sum of weights on that path.
So this is at most case.
Yes, of course. Always you're interested in minimizing your cost, right? Surely it does not make sense to have lower bounds on the amount of cost you're incurring.
Average bounds, you can have mean values.
Well, yes, you could have maybe randomized algorithms that you want to compute the expected weight of. But here, of course, like those are all just multiple variants. Here we're just discussing the version where you're looking at worst case complexities.
Okay.
Another interesting model is the one infinity model. What that means is all of your pairs UV cost exactly 1. And then some edges are infinity. What that means is you actually can't compare them. You're simply not allowed to compare them, and you're given the guarantee of a Hamiltonian path. So you're told that there's this hidden graph. The edges that are missing are the ones with infinite cost. And you're told that there's a Hamiltonian path in here. And in your question, you can ask an edge and reveal its direction. And you want to ask as few questions as possible to find the Hamiltonian path, and so on. And then there's all of many versions. You could have something like you have maybe triangle inequality is satisfied. Maybe you have something like this. There are all of these versions, and of course you want to solve the problem efficiently in these versions, and that's what sorting maybe looks like. Now, yeah. Okay, I think that's good enough. I think we can maybe stop here. I'll take any questions.
Yes, can you please explain that K-log? Can you give an idea for the K-log K algorithm?
Okay. So the idea is to use, well, a different kind of heap, really. I think that's maybe the best way to put it. You do not use this binomial heap.
But
like how did someone even motivate this binomial heap algorithm?
Yeah, I mean, okay, so the motivation was that whenever you ask these questions, you obtain these trees, right? And then you want to look for certain types of trees that would have these properties that when I remove a certain vertex. So, for example, let's think about the case where you had the second thing maximum or the first thing maximum even. So let's say the true sequence was n all the way till n minus 1. We call it 1 to all the way till n. So how would we add edges? We'll predict 1 is our maximum, and we'll add an edge from 2 to 1, and then from 3 to 1, 4 to 1. So you get this star graph, right? And now the problem with this star graph is that when I delete 1, all of a sudden, I get too many components. So it again takes a lot of time to merge them again. Right? Yes. I have up to n components now. And the binomial tree, what that helps you is it helps you to join things in a very structured way so that when you delete a vertex, very few new components show, log in new components up to. And so you can sort of merge them again. So that is the I won't comment on because it's difficult to come up with that because it is by no means easy, certainly very magical in that sense. And I did say that I was just going to define these and then we want to use these to solve the problem. Okay, right. Any questions?
So is the K log K heap also a tree heap or is it a different sort of heap completely?
It's a different sort of heap. So like binomial heaps do not work there, I believe.
Do tree heaps work or do you need a heap of a different thing altogether?
I'm not sure. I think, well, actually what you do there is you just find the largest K elements by using a linear time algorithm. So it is known that we can find the element with rank K in O of n time. There are algorithms that achieve that, deterministic algorithms, not just randomized. And once you have the rank K element, then you can just figure out the largest K elements. Once you have the largest K elements, just sort them. You get K logged.
But wouldn't it take NK turns? Like you have to do that?
No. I'm telling you that in linear time, I can discover the element with rank k.
Yeah, and you have to do that k times. So n into k, n k.
No, I'm not going to do that k times. I'm just going to do it once, right? N minus k. And then I figure out all the elements that are bigger than this. I compare this vertex with everybody else.
Oh, okay.
And then I just know the largest k elements and then I sort. That's the n plus k log. So
that's good. Also, basically, you do bubble sort only type thing to figure out instead of bubbles figuring out maximum, you figure out k maximum.
Well, are you asking about the algorithm that figures out the element with rank k?
Yeah.
Okay, so that it's very long. Well, I would love to discuss it. I think we're short on time. I mean, I could sketch out the details if people are interested. But I mean, I don't know. And also, I don't know if we have time because I think there will be a next class as well, right?
That has 23 minutes.
Yeah, the next class is at 6:30. So if people are interested, like I'm definitely interested in seeing more of this.
Yes.
Okay. So then we can sort of shortly discuss how to devise an algorithm that finds k rank in linear time. Okay.
Yes.
So first, I'm going to say this. Again, this is all very unmotivated. Okay, so first, if I have an algorithm okay, this is actually really long. I'll just write it this better. Okay. Let's first discuss a randomized algorithm for this. I think that will make it easier to motivate. Let's say you're trying to search for the element with rank k. What rank k means, just to make it clear, is if I were to order them in increasing order, if they look like this, then I want to discover A. That's all I care about. That's the element with rank k. Okay. So we're interested in finding AK, and let's say we're being given K and that list A1 through A. That's it. Always the idea is to find a good pivot. What a good pivot does is you have this approximation and you look at all things less than or equal to m. You can sort of get that in linear time. So in linear time, you can construct these two sets, stuff that is bigger than m and stuff that is smaller than m, right? Does this make sense?
Yes.
Okay. And now what am I doing? I have something like m here, and I want to find the element with rank k. So can I discover in can I just tell by looking which of these groups k will be in?
Yes.
So let me actually just include m in one of these because m could also be the element with rank k. Although we would know that, of course, if this is size exactly k minus 1, then I know m is my element. I somehow got lucky, so I can just click on that. But of course, that's not going to really happen. And so I have these two groups, and the kth element will be in one of these. How can I discover which of these it will be in?
It depends. Is the size more than k minus 1? Is the size greater than k?
Let's say this has size c. If c is less than k minus 1, then that tells me that the rank k element exists here. And can I also know its new rank in this set of elements?
Yes.
What will that be? That will just be c minus k.
Yes.
Okay. Sorry, k minus
c. Yeah.
On the other hand, if c is greater than k, then I know that the kth element is somewhere in here. And so I can just return to these processes. So now I have this recursive algorithm basically that somehow finds this nice m and is able to sort of go into one of the two. What would be the complexity of this? Let's say this has size A, so size B. At present, we have no idea on how to select m, right? So this has size A, this has size m. And what I'm doing is I'm solving this problem of size n originally, and it could go into problem size A, it could go into problem size B. And of course, the problem with this approach is that A could be n minus 1. I just chose the maximum somehow. It's not a good pivot. A good pivot would be when A and B are, they are having, so okay, let me define that. I call M R pivot if the size of A divided by the size of B is between 1 by R and R. Does that make sense?
Yes.
Okay. So for example, a 2 pivot would mean that you have all these possibilities where this could be at most twice as large as this, and this could be at most twice as large as this. So in particular, you know that both of these are between n by 3 and 2n by 3.
Yes.
Right? And if somehow I had an algorithm that in linear time is able to find an R pivot for some fixed R,
Yes.
then I can use that over and over to devise an algorithm that runs in linear time, because I have T of n equal to n plus T of n over R, or actually
NR
minus 1 by R times n. Right? I have this algorithm, O of n, of course. Right? So here is going to be a one-dimensional tree. It's just like n. Here I have 1 minus 1 by Rn. And you can just see that this is like a nice little GP that will sum out to something like O of Rn-ish.
Yes.
And that because R is fixed, this is linear.
Yeah.
So if I had some way of finding such a nice pivot, I would be done.
Yeah. But
right?
The way will also take some time, right? How will you consider the fact the way takes some time?
How will I factor in the fact?
Because consider the fact that A or the figuring out the M will also take some time.
Well, yes, exactly. So I want to do that fast. That's the point. And one way to go about it is just choose M randomly. If I choose M randomly, if I draw this strip, maybe like something like this. If I draw this strip that has like maybe n by 4, n by 2, and n by 4 in the true ordering. So there's a half probability that I select something from this strip, right?
Yeah.
And when I order, both pieces will have size at least n by 4, and so it will be a 3 pivot.
Yes.
Right? And now because I'm saying that with probability half is going to be a 3 pivot, I'm just going to keep repeating it until it is. And the point is within a few moves, I will eventually find a 3 pivot. And each step takes O of n. So in like randomize O of n times something small, I can find a 3 pivot necessarily. And because that's linear as well, that linear actually just adds in here.
Yeah.
And so the entire thing is linear, and this is a randomized algorithm. This is not deterministic.
Yes.
We can do deterministic, and that actually has 2 layers of recursion. So you use both of these sub procedures together. I'll just sketch that out as well. That has a really difficult idea and took a lot of time to find that. And in fact, what we can prove is that you have median finding algorithms. You can always find the median.
So you just basically k is equal to n by 2.
Well, yes, something like that. So you can always find the median in linear time. And the way you do that is, well, not a median, but rather an approximate median. You can always guarantee that you can find some R pivot for some R in linear time. Okay, for some real constant R. And then using that, you can figure out median. Anyway, so I'm just going to sketch out how you can find a R pivot in linear time. The way that goes is you have your sequence of n things, right? Split them into 5 groups of 5. This is called the what is it called? It's called something of the 5's algorithm.
5 is specific, like 5 is
yes, 5 is important. 5 is crucial. I mean, you could have 5 larger, but 5 is the smallest thing that works, and because it gives a lower constant, you just use it. So you have these groups of 5 up to n by 5, right? You can find the median of these.
Right. Using recursively.
So I'm going to show that I have this first algorithm that does median finding. It finds the true median finding, all right? And the second is it finds R pivot or some R that I'm going to describe and figure out just, I don't remember it. So yeah. So you have n by 5. And what I can do in each of these is I can figure out the median, right? It's actually very similar to the triangle idea you had mentioned earlier. So you find the median in each of these. And you look at median of medians. So you have these up to n by 5 things, and you use the first algorithm. I'm going to call this algorithm A, and I'm going to call this B maybe. So I use A of n over 5 steps. And that will give me my median of these medians, right?
Yes.
So if I were to place them into this table of size 5 and then by 5, I know that this is middle of the pack, right?
Yes.
Now this is larger than all of these. I can guarantee that. Agreed?
Right.
And how many elements is that?
That's n by 9n by 25.
9
9n
by
is
20.
by 9. It should be 9n by 25 only.
But is it not n by 4?
Like this is 3 by 5 and this is 3 by 5, so you have 9 by 25 of n.
Okay. So you have some R, some 9 by 25 maybe, I don't know.
Yeah.
Something like this. And now because you have something like this actually tells you that this thing for the entire thing is some R approximate, right? For
Yeah.
some R. And so you have now figured out B. So how much time did B take? B took something like B of n equal to linear time plus A of n over 5. All right?
Yes.
And now let's take a look at
5 of n over 5, right?
No. I mean, I can find the 5 things in constant time anyway. Na?
Yes.
Right? Just query everything, figure out the median.
But
So
he's going to have to figure out 5 medians. So that's going to take 5 an over 5.
no, this is like I find the median of each of these buckets of size 5, and now I have these n by 5 medians.
Yeah.
And I take the median of these medians.
Oh, okay.
Yeah.
But that's a one. But
This
but
is bigger
an
than
of
at least half.
an by 5 is the time it takes to find a median of a fifth, right?
Sorry?
An by 5 is the amount of time it takes to find the median of n by 5 numbers, right?
Exactly, because A is the algorithm that does median. I'm going to describe both. They both depend on each other. That's the point.
Okay. So, but you have to figure out these 5 medians. So that will take 5 times an of an by 5.
No.
Why no?
I mean, I have these up to n by 5 things, right?
Yeah.
And it takes me something like 5 choose 2, like 10 questions to figure out the median of each of these 5 groups. So that's 2n questions, right? And I have these n by 5 medians of these groups.
Oh, right.
And now I already have those n by 5. I just have to, I'm not repeating it over and over.
Okay. So an by 5 is the amount of time it takes to find those n by 5 medians.
No, 2n is the amount of time it takes to find those n by 5 medians. A of n by 5 is finding the median of those medians. That's
okay. Yeah.
A is median finding, right? Okay.
Yes.
So I have this algorithm first. I have this recursion. And now A of n also depends crucially on B of n. What does B of n do? B of n finds the median, right?
Yes. No, B of n finds the R. It finds the R pivot.
It finds an R approximate, exactly.
Yeah.
So B of n, sorry, no. Yeah, B of n finds an R pivot. And now if I want to calculate A of n, the actual median of n things, then we're going to use an algorithm similar to before. In fact, I'm going to generalize A of n to any rank. So I can find general rank finding. Call this general rank finding. I can find any rank. That's A of n. So of course, all of these still hold, because if I'm able to do any rank, I can certainly do median. And now if I want to find any rank, then I have this, if I choose the R approximate, then it's something like O of n again, plus something like A of 1 minus 1 by R times plus B of for finding the R.
Yes.
And if you do a careful analysis, you can figure out what the exact value of R is. And using these two together proves that both A and B are linear.
That is nice.
And because A and B are both linear, you can now look back and you can say, okay, I can find any rank, right? And so find rank n minus k. That gives me A1 till A n minus k. Actually, sorry, it should be A n minus k plus 1. Find element rank n minus k plus 1 all the way till A, and I can discover these in O of n questions then. And so I have the top k elements, and now I can just sort these in k log k questions as usual, and that's a total order of n scale. That's the entire sketch. Okay, so I think we can stop here. Any other questions?
No.
Okay. Okay, I think we can stop here.
Very cool class. Thank you so much.
Yeah.
Yeah,
Thanks a
amazing.
lot. Class was very nice.
Thanks.
Thank you.